Subscribe to our YouTube channel and press the bell icon to get the latest updates.
Last week, astronomers announced that they have detected light coming from behind a black hole for the first time. The researchers were studying X-ray emissions from the supermassive black hole at the center of the galaxy called IceWiki 1. Here, they noticed that along with the X-ray readings that they usually obtained from the front of the black hole that is facing us, they also saw flashes of light and X-rays, or what they call luminous echoes, from a part of the black hole that they initially could not identify. Soon they realized that these electromagnetic signals were coming from behind the black hole in accordance with predictions made by who else but Einstein. In this video, let's have a look at how light moves around a black hole, how black holes warp and bend space-time and light, and what it is that Einstein had predicted in his theory of relativity, which we keep saying periodically that new findings keep proving right. I'm Sandhya Ramesh and this is Pure Science. First of all, what are black holes? A black hole is a type of compact object that is left over after a massive star's death. It is an object whose density is so high, or rather it's a region of space-time where the gravity is so strong that no matter or radiation can escape from it. The boundary of the gravitational influence of the black hole is called the event horizon. We often picture black holes as these entities with infinite gravity that suck everything in from everywhere, but this is technically not true. Anything that is inside the event horizon inevitably falls into the black hole, but matter that is outside the event horizon is safe from the gravitational influence of falling into the black hole. So if a black hole of the same mass and gravitational influence were to replace the sun, nothing would happen to any of the planets or the orbits that they all are in right now. The existence of black holes was thought to be a myth for the longest time, even by renowned theoretical physicists. Then when Einstein came along, his theory of general relativity, or his general theory of relativity, described how an object with extremely high mass can bend space-time. And the easiest way that we can picture this is imagining a rubber sheet and balls of various masses and sizes on them. Light travels on the fabric along its surface, and when there's a very heavy mass, the fabric bends down because of this, and thus light bends with it. So we say that more massive objects warp space-time, which is both space and time. We have observed massive objects warping and bending light in the form of gravitational lensing. As the name suggests, it is when the gravitational pull of a massive object acts like a lens, bending the light and distorting the light that is coming from another object that is behind it. As light gets bent by a gravitationally strong body, it tends to produce an apparent image displacing the location of the source. Sometimes the warping of light can even cause duplicates of the source, causing us to think multiple copies of the same source object also exist, and so on. So this is the prediction that Einstein's theory of relativity made that keeps getting proven right. He basically stated that the basis of general relativity is that more massive objects warp spacetime. So whenever we make observations that show the warped spacetime in the form of bending of light or any other form of electromagnetic radiation, Einstein is effectively proven right. While we've observed things like gravitational lensing before, this is the first instance that we are seeing of radiation echoes or flashes from behind the black hole. This is also a prediction that is made by the theory of relativity, that we should actually be able to see radiation from behind the black hole. The team of astronomers, mainly from Stanford, were actually observing the black hole to understand a feature of the black hole called its corona. As matter and gases swirl and fall into a black hole, the matter spins around in the form of a flattened disk, and all the material superheats in the process, becoming magnetized plasma as electrons are ripped out of their atoms. At the inner edge of this disk, closest to the black hole, with temperatures millions of degrees, a lot of X-rays are produced. The magnetic field here arcs high above the black hole and then eventually snaps, and this releases the X-rays from the corona into space. This region of superheated gas and material and plasma that glows brightly in the X-ray wavelength is called the corona of the black hole. We've observed the corona of a black hole before, although we don't understand much about it just yet. It is dynamic and its properties keep changing constantly. Astronomers have in fact just last year in 2020 observed the corona of a black hole at the center of a galaxy rapidly fluctuate in size and brightness over a period of just hours. MIT astronomers watched the corona disappear and then reappear over hours and over months. The result was fluctuation in the black hole's brightness, dropping it by a factor of 10,000 in less than a year. Such luminosity changes are actually thought to occur over a period of millions of years. But astronomers observed the corona disappear and then new matter being pulled in from the outer portions of the accretion disk or the swirling disk of gas and matter around the black hole, and then once again see the release of high energy X-rays close to the event horizon, forming a new corona. This is the phenomenon that the team of scientists from the new study were also attempting to study and understand. Theoretical physicists are still unsure about why a corona forms, but a likely reason is because of the magnetic field lines that run through the accretion disk or the swirling disk of matter around the black hole. In the outer parts of this disk, the lines of the magnetic field are in their normal configuration. But closer to the event horizon and closer to the black hole, there is intense energy being released as particles and matter spins faster and faster towards the black hole. The magnetic field lines here can twist and bend and break and also reconnect and tangle up in the process. This process of tangling up of the magnetic lines and their snapping can also add more energy and spin to the matter that is already glowing so hot. This is very similar to what happens on the surface of our sun, and that is why the term corona was also borrowed from solar physics for the black hole. We study the energy released by black holes to understand how other galaxies form around them, as powerful processes stemming from powerful objects like black holes feed other forms of matter accreting and forming structures in the universe. So when studying this data of the corona of the black hole, a series of bright flashes of X-rays were observed that were smaller and of a different color or wavelength than the bright flares that were being recorded from the front of the black hole. These X-ray flashes were consistent with signals from being behind the black hole. And the reason they come to the front is because the warping is bending light and also twisting magnetic fields. So the X-rays produced by the black hole were actually reflected off the edge of the black hole's accretion disk, and they were then bent to go around the black hole by its own gravitational field, which bent the magnetic field lines. So the X-rays moved along these magnetic field lines around the black hole, subsequently being visible as flashes in the front, reaching telescopes here on Earth. Two different space-based telescopes which were built for detecting X-rays in space made these readings. One was the NuSTAR, which is operated by NASA, and the other was the XMM Newton, which belongs to the European Space Agency or ESA. This is the first time we made an observation like this of electromagnetic radiation coming from behind a black hole. This has also gone on to confirm what we already understand about supermassive black holes and how they behave in the universe, thanks to the theory of general relativity. Studying more X-ray echoes from behind black holes and understanding these dynamic processes around such extreme objects could help us answer some of the biggest questions about the nature of this universe that we inhabit. What happens around black holes to matter and radiation, how black holes can birth and grow full galaxies, how less massive black holes can grow on to become supermassive black holes, and finally, how such objects, which are singularities where laws of physics completely break down, are even created in the first place.